It's always a good idea to have a plan when repairing a computer. However, sometimes the plan points one way and your gut tells you it's something else. And this is one of those times.
Hello and welcome back to Noel's RetroLab. Today we're going to take a look and try to repair this Oric computer. This one in particular is an Oric Atmos, which is a very compact and has a very classy color scheme and a great keyboard. If you encounter the Oric one, which is pretty much the same computer but with a different case and keyboard, you'd be forgiven for thinking it was a ZX Spectrum clone. It was released in September 1982 by Tangerine Computers, yes, that's an actual company name, in the UK about 6 months after the ZX Spectrum launch, which makes it look more and more suspiciously like a clone of the popular Sinclair computer. But as we're about to see in a second, when we open it up, it's nothing further from the truth. The model we're going to be looking at today, the Atmos, was just an outside refresh, and that was released 2 years later in 1984. The fact that a lot of you probably have never heard of Oric computers means they failed at the UK marketplace. Interestingly, they were quite popular in France during a certain period of time, and they even spawned a series of Eastern European clones like the Pravets 8D. So what does it have inside this little package? Oh, that's interesting. The board is mounting pointing down instead of pointing up. That means that I can flip the computer and the keyboard and have access to the board. That's an interesting choice that I hadn't seen in other computers. The biggest surprise, other than the absolutely massive speaker, is the CPU. This is a 6502. So that just shattered any illusions of similarities with the ZX Spectrum. That's the CPU you find in computers like the Apple II, the Commodore VIC-20, or an Atari 8-bit. That's some interesting company. Over here, we have 16 kilobytes of ROM with the basic interpreter and system functions. It's interesting that the board has some empty spaces to allow for different configurations in multiple smaller chips. Fortunately here, we have just a single 16 kilobyte ROM, so it will be easy to replace with a 27C128 EEPROM if we need to later, for example. Down here, we have 8 4164 DRAM chips. Those are very common in other computers at the time. Each of them has 64 kilobits of data, so we have a total of 64 kilobytes of RAM. Wait a minute. The Oric specs are actually listed as 16 kilobytes or 48 kilobytes. What's up with the full 64 kilobyte of RAM? Are these like half-defective chips like the ZX Spectrum? Not at all. They're actually fully functional. It's just that they decided to make the design super simple and mostly super cheap and simply overlay the 16 kilobyte ROM on the addressing space. That seems like a really bizarre decision, but I suppose the reasoning was that 48 kilobyte is enough for everybody. And besides, that's what the ZX Spectrum was doing at the time. And there, towards the middle, we have the ULA, the true heart of the Oric. Like the ULA in other systems, it contains all the logic that makes the Oric unique. It takes care of coordinating RAM access, displaying graphics, etc. This is clearly a custom chip, so I really hope it's working correctly because it may be hard to get a replacement. There's also an AY sound chip, which is the same as the Amstrad or MSX or even the later ZX Spectrum computers, but that's pretty good for a computer that came out in 1982 and that was directly competing with the ZX Spectrum one-channel beeper. The rest is all pretty standard stuff, an I/O chip, some logic for multiplexing addresses, and some more composite video generation. All that in a neat little package. Okay, let's see what's going on with this Oric. I was told it wasn't working, but I don't remember any more details. Before we turn it on, I see there are some modifications on the board. There's this cable running along the front, and there's a resistor and a capacitor soldered in the back. At first, I wondered what these mods were and whether they were made at the factory or afterwards. It turns out the Oric service manual comes with a list of 5 or 6 recommended modifications from the factory, which includes these, so it's probably fine, but I'll keep them in mind just in case it affects any problems we may have. I'll connect the video cable and the 9-volt power supply. This one is center positive, so don't reuse the ZX Spectrum on this one. And when I power it on, we get about 600 milliamps, which seems reasonable, but we have no image signal at all. As usual, let's start checking voltages. The 9-volt DC input voltage is converted into 5 volts through a regulator, but here's a weird quirk of the Oric. You'd expect it to use a 7805 regulator, pretty standard for the time, but instead they use a 7905 regulator, which generates -5 volts, but then they simply hooked it up so that the positive output terminal goes to ground and the negative to the -5 volts. So yes, they are generating 5 volts, But why do it in this convoluted way? Did they have a great deal on 7905 voltage regulators? It's not a big deal unless you start mixing voltages from external sources and find out the hard way that ground on the external power supply does not correspond to ground on the computer itself. So watch out for that. In any case, the voltage looks around 4.9, which is great, so that is not the problem. The next step, whenever we don't even get any kind of video output signal, is to check the clocks. Because without clock signal, nothing in the computer will be working, so that's a good theory. Let's have a look at the clock signal into the CPU, and that looks okay-ish, although it's a bit unstable. This should be solid, so that's a bit odd. The output clock signal generated by the CPU, it looks about the same, kind of like a little shimmery. Not sure what's going on in there. So let's go to the source of the signal then. On the Oric, the clock signal is generated from a 12 MHz quartz crystal. The oscillation is enhanced by feeding it through a couple inverter gates using a 74LS04 and a capacitor. All pretty standard stuff. So looking at the output of the inverter, we should see a very regular wave of about 12 MHz. It's usually not totally square at this point, more like a triangle wave. But instead we get this really weird mess. What's this? Not only is the shape ugly, but the period is very irregular. And poking around, the rest of the clock signal circuit shows similar irregularities. Could the quartz crystal be faulty? The inverter looks fine just by looking at some of the other signals, but could be that gate. Really, the clock signal looks bad, but is that enough to cause no video out at all? I have to admit a pretty embarrassing mistake. Probably some of you Oric diehards already noticed it though. Because the board is mounted pointed down, I had to flip the computer. And that means the orientation of the ports has changed. Seen from the top, the video connector is on the left, but once I flip it, it's on the right. But out of habit, I connected the video port to the right, even though they were flipped. And how is that even possible? Aren't they using different DIN connectors? They are, but so badly chosen that the monitor connector, which is a DIN 5, fits perfectly in the cassette connector, that is a DIN 7. Bad Tangerine designers, bad. Hopefully I haven't blown anything, but I bet now we're gonna get some video signal. And yeah, there you go. We do have a video signal, and it looks really shimmery and uneven. It's actually kind of pretty though. That'd be a fun effect to do in some kind of crazy demo. In any case, this pattern seems to match what we're seeing with the uneven clock signals. So I think this strengthens the theory that we probably have a faulty quartz crystal. Let's replace it and see if anything changes. Okay, there we go. And now let's see if there's any difference in the clock signal. Oh yeah, that looks much better already. Yeah, check it out. Now that we're zoomed in, there's a totally steady 12 MHz signal. And the clock signal going to the CPU? Yes, that looks perfect. And the output clock signal too. So yeah, that was definitely the problem, which is not that common to have quartz crystals fail. So let's look at the video out now, and yeah, that's much more encouraging. We have at least some steady graphics on the screen. That probably means the ULA is working, since it's in charge of generating the video signal. And really, this looks like a very typical RAM problem. So let's investigate the RAM. Maybe we'll be lucky and we'll spot something obviously wrong. Here, I just want to see if any of them are stuck at 0 or 1, or maybe showing some particularly ugly signals. And that might be an indication that that chip is faulty. But here, they're all looking pretty much fine. A quick check at row address signal and column address signal, or RAS and CAS. And yeah, I see that they're both being triggered, so things seem generally fine. The next, easiest test to do, especially since the Oric has been on for a few minutes, is to check if any of the RAM ICs gets particularly hot. Nothing seems to stand out to the touch. And if I pull out the laser thermometer, they're just warm, but nothing out of the ordinary. And yes, one of these days, I'll get a thermal camera. I'm looking forward to that quite a bit actually. So we weren't lucky and we don't have anything really obviously faulty, so we'll have to move to more sophisticated methods to narrow down what the problem is. A Diagnostics ROM could be really helpful, and as luck may have it, there's one available for the Oric. And to make it even easier, the ROM chip is already socketed, so I can just burn it into a 27C128 and drop it in. I love it when it's that easy. However, what's not quite as straightforward is the Diagnostics ROM itself. On a Z80-based computer like the Amstrad or the ZX Spectrum, you can do quite a bit even if all of the RAM is faulty. In the Diagnostics ROM I wrote for the Amstrad a while ago, I even drew screen patterns with the numbers of the faulty ICs even if all the RAM is completely removed. On the 6502, things aren't that easy. You're really crippled without zero-page addressing because there are so few registers. So this particular diagnostics program is mostly intended to be used with a special extension board that will light up specific LEDs with different codes depending on what happened. Normally, I will get the PCB printed for the Diagnostics ROM. And what better place to do that than with today's sponsor, PCBWay. If you go to PCBWay's project website, you get access to lots of public projects available right there. You can type Oric and what do you know? The Diagnostics PCB project shows right there. From here, you can click the button to order it and have it in your hands in a few days, or you can be like me and forget to do it until the last minute, and I need to make do without the custom PCB. Oops! The documentation for the diagnostics test explains that if the initial RAM test fails, you'll get a certain pattern on the address bus. If that passes, but the more exhaustive RAM test fails, then you'll get a slightly different pattern. And then I believe that even if that one passes, then it moves on and displays all the information on the screen. So first of all, let's turn it on and see if we get anything on the video out. And yeah, that's a no. Same as before. Alright, since we have an oscilloscope, let's check those address lines. And yeah, that looks right. A0 and A1 have quickly alternating signals, A2 is high, and the rest of the bits until A7 are all low. So this is really helpful. It removed several major components from the potentially faulty list, and we know for a fact that the CPU is working correctly because it's executing the ROM code. At the same time, we know that the address and data buses are all working fine, or at least as far as the ROM goes. And most importantly, the test is telling us that the RAM is faulty. Not just slightly faulty somewhere, but that the very first test it does failed. Unfortunately, the diagnostics test didn't tell us which of the chips is actually faulty. But since I have a desoldering gun, I'll just go ahead and swap them all. So that should be really easy from here, right? Right? Instead of just blindly replacing them, I'm curious to find out how many of them were faulty. So I'm going to run all 8 chips through the RetroChip Tester Pro. I'm taking bets. How many do you think will be faulty? I'm going to go with a single one, but we'll see. If the Oric was zapped with the incorrect power supply, maybe they're all damaged. Wait, what? Is this possible? All RAM chips pass the test? I guess this is not gonna be as straightforward as I was hoping for. So time to have a close look at the RAM circuit. This is all very similar to a lot of other 8-bit computers. ROM access is very straightforward because all 16 address lines are fed directly into the ROM, and then it outputs all 8 bits of the data at that address. RAM access, however, takes a little bit more work. RAM chips of this size can only take 8 bits of address at a time, so the computer needs to select half of the address bus, pass it to the chip, and tell it to read it by setting the RAS line, and then pass it the other half of the address and set the CAS line. Only then does the RAM output the bit corresponding to that address. In order to select one half of the address bus or the other, the Oric uses 2 demultiplexers, which with some signals from the ULA can select the lower or upper half of the address bus. Clearly, if one of those demultiplexers is faulty, reading from the RAM would not work at all, so that's a good starting point. Just checking the inputs and outputs of the demultiplexers, I don't see anything obviously wrong. They seem to be working. There's activity going on in all of them, and they're not stuck. So they could still be faulty, but not in a way that we can trivially see it. So I think it's best if we also desolder those and try putting new demultiplexers. But before, let's test them with the chip tester again. And oh no, they're both passing. So that wasn't it. What's going on in here? Just to be really sure, let's put new demultiplexers anyway, and nothing. We still get garbage screen. So this is really puzzling. I'm really surprised it wasn't the RAM or the demultiplexers. It can still be a few other things, but each step gets a bit more unlikely. Just to be really sure, and because it's so easy, I'm going to just put new RAM. I know we've tested all the RAM chips and they all passed, but you just never know. Maybe they pass in the tester, but the Oric is having some really tricky timings or something like that, and what makes one of them fail. So I just added new RAM chips for my stock, and when I turn it on, no, it fails again. The pattern in the screen changed quite a bit, but that's actually normal. That's the ULA displaying the contents of uninitialized memory, and these chips must just have different default values than the other ones. Okay, I figure it was worth a try at least. I think the next most likely thing to be failing is the ULA itself. It seems to be generating a correct video image, but part of it could be faulty, and maybe it's just not generating the correct RAS, CAS, or even read-write signals that interface with the RAM. I've seen all those signals on the oscilloscope, but maybe their timings aren't quite right. I know it's a little bit of a stretch, but we're getting at the bottom of the barrel as far as possible causes for this problem. This also gave me a chance to look into this mod over here. This is called the 63B modification in the service manual, and is described as helping with initialization on power up, which may be related to what we're doing here. It basically adds a pull-up resistor to the clock signal generated by the inverter, so I suspect that some versions of the ULA were just not detecting the clock signal correctly, and this was helping with it. I'm going to leave it in place for now, but I don't think it's strictly necessary, so maybe I'll pull it at the end. Fortunately, I had a spare Oric ULA around from the time that I bought my own Oric, so we can use that for testing. And nothing again, still the same pattern. This is getting really strange now. We seem to have eliminated almost every chip involved in the RAM reading process, and it's still failing. And when I say almost, it's because there's still one chip, one inverter chip that's involved in inverting the read-write signal, but it's also the same chip that inverts the clock signal. So of course I had to change it just to make sure, and it made no difference. So now what? Let's have a look at what the diagnostics program is doing exactly, or at least how it starts. We know it's working correctly because the pattern on the address bus is showing up, but maybe this will give us a hint on how to test things further. It turns out the start of the code is very simple. After a bit of initial cleanup, like turning off the interrupts and setting the stack, the code simply writes an alternating bit pattern to address 0, reads it back, compares it, and then does the same thing again on address 1. That's the whole quick RAM test. If that passes, then it moves on to something more comprehensive. So knowing that, I thought about setting up the logic probe and trying to capture the bus traffic to match it to that pattern, but that's always been really difficult to do with an 8-channel probe like I have, and then with memory refresh and video generation going on in addition to that, it can be really tricky to match the signals. So instead, that gave me an idea for something that we can check. It looks like the code starts executing, and just a few instructions later, we do a RAM write, and then, if that went well, another one. So maybe we can try to capture those signals and see if we can get that far. I'm going to hook up channel 1 in yellow to the read-write signal. It will go low when we do a write. Channel 2 in blue is going to be the sync signal of the 6502, which goes high every time the CPU fetches an instruction opcode. Oh, interesting. So we see one write pulse in here and a few instruction fetches, which seems to match what we expected from the source code pretty well. However, I don't like that ramp up curve at all. It makes it look like the computer is starting to execute the ROM before it's fully powered on. I'm going to try it again just to see if it was a coincidence. And yeah, exactly the same ramp up. So this makes it seem like the very first read fails and it doesn't try to do a second write. But I wonder if that could be related to things not being completely powered at the time it does that. So to test that theory, I'm going to add a reset switch to the Oric. I have this spare one from the ZX Spectrum Plus that will be perfect. I'll hook it up between ground and the reset pin on the 6502, which is pin 40, and that way I'll be able to reset everything once we're fully powered and see if that makes a difference. Okay, let's go ahead and try it. And yeah, we still get the same thing. This time we don't get that ugly voltage ramp up, but we get a single write and we fail the test. So that wasn't it. I am totally stumped at this point. I'm actually skipping over all the checking of connections that I did to make sure that there were no breaks in the tracks and rechecking all the things that I had checked before, and none of that made a difference whatsoever. Occam's razor tells us that the simpler theory for a problem is likely to be correct. And this sure smells like a plain RAM failure. The only problem is that I've already checked that a bunch of times in a bunch of different ways. But I'm still not convinced it's anything more complicated. So before we go off the deep end and start getting the logic probe and do a full bus analysis, I'm going to do one last test. I have an Oric Atmos over here for my collection that's working perfectly. So I decided to desolder one RAM IC and use that to test each RAM chip from our non-working Atmos. If there's a bad IC, we should be able to spot it right away. So far, everything is going fine. And oh wow, this one doesn't work anymore with this one. What? Let me try reseating that chip. And nothing. So this one looks to be faulty. How is that even possible? For now, let's mark it and check the rest. And yeah, that's the only one that gave us trouble. So with that questionable IC on our Atmos, okay, we have the usual failure pattern. But if I change it with a different one, oh wow, now it works. And we see the diagnostics test once it starts using the screen. You can even press that big button in the bottom to go to the next step of the diagnostics. Oh wow. Okay, I'll swap out the Diagnostics ROM and put the original ROM back in. Yeah, it works perfectly now. And just to make really sure, let's run a game on the Oric. In this case, I'm going to be running Blake's 7, a modern homebrew game made by my friend Chema, and it's one of the best games you can find for this platform. It's totally amazing that the Oric can do something like this. Can you imagine something like this in the 80s? So we can't just stop here. That would be like one of those movies that wraps up a mystery in a totally illogical way and says at the end. So let's try making sense of what happened here. I did test every RAM IC here with the Retro Chip Tester Pro and they all passed. I also replaced the RAM ICs with other ones and the Oric was still not working. So let's go back to the Retro Chip Tester Pro. Did I accidentally do something wrong during the testing? I actually went back and looked at the footage I recorded, and I did every single chip, so I didn't accidentally skip one or use the wrong setting or anything. It's all recorded in film. Well, in a digital camera. So let's try it again to be sure. And yeah, it reports it as passing again. What is going on? I talked to Stefan, the designer of the chip tester, and in a more recent version of the firmware than the one I have, he improved the DRAM tests. He slightly tweaked the timings in which RAS and CAS are deselected to make them more compatible across different chips. So let me quickly upgrade to the latest version of the firmware. And let's try it again with the same chip. And oh wow, now it's reported as failing. It's pretty amazing that this chip works fine with a slightly different combination of signals, but it fails with the exact timings of the Oric. That's pretty unusual to get such a subtle failure on a chip. Also, by the way, this doesn't mean that the Retro Chip Tester Pro was faulty. What it was doing in the earlier firmware was still totally within the normal specs of the chips. So it's just this particular timing that affects this one chip. Just to get another reference, I'm going to throw it in on an Amstrad CPC and run the Diagnostics ROM I wrote a while back. And with that chip, yes, the Amstrad also detects it as faulty, and in this case, it even reports exactly which chip is failing. So the last question is, how come that when I put in all new DRAM chips, it also didn't work? I guess I must have been extremely unlucky and one or more of those chips were not working. I thought I had tested them all before, but they either also had that weird timing variation, or they simply developed a fault since they were in storage, maybe through static electricity and built up and a discharge. So yeah, I think I was just pretty unlucky with this particular combination of factors, but at least it made for an interesting dive through the Oric memory internals. And after this, I feel that I understand the architecture much better than I did at the beginning. So the next Oric repair, whenever that is, should be a lot faster. Anyway, I hope you enjoyed this video. I'm hoping to do other videos on the Oric computers in the future, including one of the most unique features about it, its graphics system. Any questions or comments, let me know in the comments as usual, and I will see you next time.
If you enjoyed this video, please consider supporting Noel's RetroLab on Patreon or joining the membership on YouTube. Not only is that the best way to support this channel and allow me to continue making more videos, but you also get some extra perks like early access, ad-free videos, and more. Thank you again to all the supporters. See you next time.